Sir Anthony J. Leggett isn't your typical Nobel laureate. Before mastering quantum physics, he mastered the classics at Oxford. This slide illustrates the philosophical physicist's unique path. Notice the interplay, ancient Greek philosophy woven between the Schrödinger equation and the BCS Hamiltonian. Leggett spent his career mapping the fragile boundary between our everyday reality and the quantum realm. He didn't just calculate, he contemplated. His journey from greats to the Nobel Prize reminds us that the deepest mysteries of the universe require both a physicist's precision and a philosopher's soul. We typically imagine a wall between our morning coffee and the microscopic world of atoms. Sir Anthony Leggett spent his life tearing that wall down. His legacy is a refusal to accept a divided universe. After solving the complexities of superfluid helium-3, he pivoted to a dangerous question. Does quantum weirdness stop where the naked eye begins? Using anomalous data as his fuel and philosophical rigor as his guide, Leggett challenged the status quo. He didn't just calculate equations, he fought to prove that the macro world is just as mysterious as the micro. Leggett's path was anything but linear. It began in a 1938 Surrey garden, digging holes and dreaming of exploration. By the mid-50s, he was immersed in Oxford classics, seemingly worlds away from a laboratory. The pivot was pure serendipity. A bored priest taught him advanced math, and then Sputnik changed everything. The 1957 launch triggered a scientific gold rush, providing the rare scholarship that allowed Leggett to start over. With zero background in science, he took a second degree in physics at Merton College, proving that the greatest explorers often start in the most unexpected places. Gemini said, "What happens when you merge the mind of a classicist with the tools of a physicist? You get the philosopher's toolkit." On one side, Leggett's training in greats at Oxford gifted him with skepticism and rigorous logic. On the other, the physicist's mastery of advanced mathematics. But the real spark was his reaction to the unnatural, those outrageous experimental results that most would ignore. By viewing the world from non-conventional perspectives, Leggett used philosophy not just to think, but to define what is objectively correct, turning anomalous data into groundbreaking theory. Gemini said, "Enter the superfluid problem." For decades, we understood helium-4, the common isotope that flows without friction at nearly absolute zero. But its lighter sibling, helium-3, was a different beast entirely. In 1972, Cornell researchers hit a wall. They found helium-3 behaving in quote, outrageous ways, exhibiting two bizarre new phases with mysterious magnetic signatures. The established models for helium-4 were useless here. The physics world was stumped by this quantum anomaly, creating the perfect stage for a scientist who specialized in looking at the world through a non-conventional lens. To solve the mystery, Leggett imagined a quantum dance. He formulated the theory of Cooper pairs for helium-3, but with a twist. Think of the atoms as modern dancers on a crowded floor. Even when separated by dozens of other people, two partners remain in perfect synchronization, mirroring every move. This coordinated choreography creates an anisotropic pairing, a structured state that finally explained those bizarre magnetic signatures. Leggett didn't just guess, he predicted new phenomena that experiments confirmed almost immediately, proving that even in a crowd of billions, quantum harmony prevails. Decades of intellectual bravery culminated in the highest possible honors. In 2003, Sir Anthony Leggett was awarded the Nobel Prize in Physics for his pioneering work on superconductors and superfluids. A year later, he was knighted by Queen Elizabeth II. These awards were more than just personal triumphs. They were a validation of his unorthodox methodology. Leggett proved that a background in the classics and a refusal to ignore outrageous data could reshape our understanding of the universe. From an Oxford student of philosophy to a giant of modern science, his journey remains the ultimate validation of a curious, multidisciplinary mind. Leggett's brilliance wasn't limited to superfluids. He also tackled the holy grail of modern physics, high-temperature superconductivity. While others were lost in trillions of compound combinations, Leggett provided a theoretical map in 1986. He proposed a specific test for the symmetry of these materials. In 1993, this led to the physical proof at UIUC. Experiments confirmed that cuprates possess a unique D-wave symmetry, behaving entirely unlike conventional superconductors. Once again, Leggett's ability to provide the underlying architecture allowed experimentalists to see what was previously hidden, bringing us one step closer to room temperature efficiency. Finally, we arrive at Leggett's next frontier. We've long accepted that atoms follow quantum rules while cats follow classical ones, but Leggett dared to ask, where is the breaking point? His mission was to push quantum mechanics out of the subatomic shadows and into our everyday world. Paradoxically, his ultimate hope was to see quantum theory fail at the macroscopic level. He believed that if it breaks, a new, currently inconceivable theory must take over. By testing Schrödinger's cat in the lab, Leggett wasn't just solving physics, he was searching for the next great revolution in our understanding of reality. In 1985, Leggett and Anupam Garg set a trap for our common-sense reality. They developed a framework to test if macroscopic objects follow two intuitive rules: macroscopic realism, the idea that an object is always in a definite state, and non-invasive measurability, the belief that we can observe something without changing it. If an experiment violates these inequalities, one of these pillars must fall. This wasn't just math, it was a way to scientifically ask, is the moon there when nobody looks? Leggett forced us to confront the possibility that the rules of the microscopic might govern our everyday world after all. The trap was set, and the verdict is in. Common sense has lost. Initially proposed using skewids, Leggett's inequalities have now been tested across qubits, photons, and nuclear spins. The results are consistent and startling. Quantum mechanics fiercely violates the inequalities. The implication? Our everyday realism is an illusion. We are forced to accept a world where macroscopic objects lack defined states until they are observed, or where the simple act of looking fundamentally alters reality. As the data shows, there is no safe boundary. In the quantum universe Leggett mapped, there really is no moon when nobody looks. In summary, Sir Anthony Leggett's career was a masterclass in redefining the rules of reality. As we see in this final comparison, he proved that the probabilistic and disturbing nature of the quantum world isn't just a subatomic quirk. It's the fundamental matrix of everything we touch. By challenging the, quote, predictable and non-disturbing assumptions of classical physics, Leggett bridged the gap between the invisible and the everyday. He leaves us with a universe that is far more unified and far more mysterious than we ever dared to imagine. The classical world hasn't disappeared, it has simply been unmasked. While Leggett's work laid the theoretical foundation for quantum computing, he remained a quintessential skeptic of its practical arrival. He agreed that if quantum mechanics holds at all scales, a functioning quantum computer is possible. However, he famously warned of the, quote, price tag. He believed the engineering hurdles and financial costs might eventually outweigh the societal benefit of factorizing massive numbers. For Leggett, the thrill of physics was always found in tangible, observable data, the strange way a liquid flows or a magnet hovers, rather than the abstract promise of a silicon chip. The guiding principle of Leggett's life is the primacy of experiment. While modern physics often retreats into the elegance of pure mathematics, Leggett remained anchored to the messy reality of the laboratory. He believed that nature's most profound secrets aren't hidden in beautiful equations, but in the anomalous data that refuses to fit our models. For Tony Leggett, a theory was only as good as the experimental fire it could survive. His legacy is a call to all future scientists. Don't just admire the math, listen to what the physical world is actually trying to tell you. In the end, Sir Anthony Leggett's life was defined by the courage to be curious. He never lost that childhood spark of digging holes to see what lay beneath. From the libraries of Oxford to the podium in Stockholm, he remained a steadfast explorer of the unknown. He didn't just accept the world as it was described to him. He interrogated it with the precision of a physicist and the wonder of a philosopher. His journey reminds us that the greatest discoveries aren't found by following the crowd, but by having the bravery to ask why, when the rest of the world is content with how. In the twilight of his career, Leggett remains a titan of intellectual honesty. Whether lecturing in Illinois or engaging with the global scientific community, his presence is a bridge between the classical past and the quantum future. This image captures the essence of his journey: a mind that never stopped wandering, a spirit that never stopped questioning, and a man who remained a steadfast explorer until the very end. His life teaches us that science is not a destination, but a continuous, courageous dialogue with the unknown. He leaves the door open for the next generation to step through.